we left off Friday talking about the SN2 mechanism, and we talked about a bunch of different stuff. We talked about the rate law, the inversion of stereochemistry, solvent, the types of substrates that prefer SN2, or the type of substrates that the SN2 mechanism prefers, which is mostly primary and secondary substrates. It can happen on other substrates, but it'll never happen on a tertiary. So in that bottom example, let me erase this. Right, in that bottom example, the substitution is going to always happen where your leaving group is. Right, so that's the group that's going to get substituted. So this would be my nucleophile, and then this is my substrate. All right, so when I do that, and then DCM is a aprotic solvent, dichloromethane. All right, so when I do that reaction, what I'm doing is, if it's a substitution, is swapping out the leaving group with the nucleophile, whatever the nucleophile is. All right, let's look at the SN1. SN1 is different, right? Remember the SN2, the substitution step is concerted, right? Everything all happens at the same time. SN1, stepwise, and it prefers secondary or tertiary carbons, right? You can also throw in, based on the list I showed you on Friday, allylic and then benzylic. Carbons, right? The reason why those are preferred is because of the carbocation intermediate that the mechanism goes through. And then if you notice, it also prefers protic solvents. Right, there's a reason for that. We're going to discuss it. It still has to do with solvation, but the difference with this mechanism is what gets solvated.
So they don't have aprotic solvents, they have protic?
Say that again. For SN1, yes.
Okay.
That's one of the ways you can tell what the mechanism is going to be, is by what solvent it's in. All right.
Mm-hmm.
So let me show you first the products, and then we're going to talk about the mechanism and what the protic solvent does and why it prefers tertiary carbons and all that stuff. So obviously it's a substitution. So this is my leaving group. It's a very good leaving group. And then this is my nucleophile. Substrate. And so for the product, let me move that. Right, that's the substitution product plus bromine, Br minus. All right, I'm gonna add a page in right quick so I can go through that mechanism without having to try to squeeze it in somewhere.
Dr. Russell?
Yes.
I looked on this assignment. Are there any highlighted, or are we doing any?
Are we doing all of this?
Not meant for us to, like to submit.
Yeah. Or we're doing all of them. I think you're missing the idea of a flipped classroom is to do the work during class. There's no necessarily no homework unless I say, hey, finish this or do this.
Okay.
So we're going to go through a lot of these. They're highlighted ones on the back, on the back pages, like back here. Some nice little breeze that just blew through here. Like back here, we'll pick problems to work from through here.
Oh, okay. Okay. I just wanted to make sure.
All right, so for the SN1 mechanism, right, the first step is the loss of leaving group. Right, that's always your first step for SN1. Right, that's the rate determining step. That's the slow step. So again, if I want to speed the reaction up, I can do three things, but one of them I'm not going to do. I can add a catalyst, which I'm not going to do, or I can use better leaving groups, or I can use a substrate that tolerates a carbocation intermediate.
And that would help speed it up,
Yes.
right, again?
Yes.
Okay.
Right, so that rate determining step. Right, that's how you can increase the rate. Use a better leaving group, or use a substrate that when the leaving group leaves, it gives you a stable carbocation intermediate. All right, so once the leaving group leaves, you get a tertiary carbocation in this case. And then, and this is the step where you have nucleophilic attack. So OCH3, and this is negative. It's going to come in, boom, attack the carbocation, and then you get your substitution product. All right. So one of the things that the protic solvent does, remember I told you if you use a protic solvent for SN2, what happens? Anybody remember?
You said if you use a protic solvent, what will happen?
Mm-hmm.
It's not
You're
good.
doing an SN2.
Does it make a salt?
What's going to happen?
Does it make a salt?
No.
Is it because they can't donate H plus? I'm trying to see.
No, a protic solvent can donate H plus.
They
so can. If you use that for SN2.
Oh, that's aprotic. I'm tripping.
It's going to, remember the term I gave y'all, solvation? It's going to solvate or surround the nucleophile.
And then it makes it weaker.
I'm trying to find my notes. But...
Sorry, I erased it. I know I talked about it though.
You said that it'll surround the nucleophile, then it'll make it weak.
Right here. When I talked about solvation, like if you use a protic solvent, the protons are going to surround the nucleophile and lower the energy. They do the same thing.
Oh, shit.
They do the same thing to this leaving group. That's why this prefers protic solvents. So it's going to solvate. Uh-oh, how did that happen? Zoom. Start reshare my screen. Sorry about that. Come on. Technology, man. I'll tell you what.
How's your weekend, Dr. Russell?
It was good. It was actually really good.
That's good.
I didn't cut grass. I didn't clean up. Nothing.
No, that's right.
You need that sometimes. Oh, man. I don't know why the screen sharing. Let me see something. Let me close this app out. Close all this other crap that's on here.
All these questions, yo.
All right. Try it again. There we go. All right. Sorry about that. So the concept of solvation, it also applies for your leaving group. So when the leaving group leaves, the product solvent is going to solvate it, stabilize it. That's going to make that happen even faster, right? So that's why we use product solvents with the SN1. And the key characteristic is that when this happens, the rate determining step is the loss of the leaving group. We talked about the stereochemistry, and since we already kind of studied stereochemistry, let me give you an example.
Dr. Russell?
Yes.
What did I say before you came down? I said a product solvent will...
No, product solvent.
No, I'm saying like product solvent will...
Solvent.
Oh, solve it. Okay. Thank you.
Yeah, that's a good thing. Solvating the leaving group is good. Solvating the nucleophile is bad. But for this reaction, the nucleophile doesn't matter. So because we know that the rate determining step is loss of leaving group, so that the rate, when we write the rate law, it's a one-term rate law. It's just K times the concentration of the substrate. So the leaving group is not involved in the rate determining step. So it doesn't matter if it's solvated or not, because that's probably going to get solvated some too, but it doesn't matter. What was I going to say? Oh, about the stereochemistry. All right. So let's say we have we're using a allylic substrate. An allylic substrate, something like this. And I'm gonna use a tosylate. We'll talk about that later, what that is. It's a really good leaving group. All right, so I'm gonna use that plus I'm gonna do SCH3.
Is this an example? There's another SN1?
Yes.
Okay.
And I'm gonna do this in water. All right, because again, that product solvent is a giveaway. If you're doing it in a product solvent, it's either going to be SN1 or E1. Right. So when I react this, what you'll notice is that now I'm getting two different products, right? Another key characteristic of the SN1 mechanism is racemization.
What makes it have two?
Right? You said why do I get two products?
Yeah. Like what made them have two?
Right. So the first step is loss of leaving group. Is that right?
Right.
So when I lose a leaving group, let me change colors right quick. When I lose the leaving group here, what I'm left with is this carbocation intermediate. Is that right?
Mm-hmm. Oh, and then.
So then the sulfur can attack either side.
Oh, either side. Okay. That's why there's two.
I can come here, or
Go in the back. Okay.
it can come from here. So that's going to give you two different products.
Gotcha.
All right. Any other questions about the SN1 or the SN2? So we know the rate law. We know the stereochemistry. We know that the mechanism, one is concerted, one is stepwise. And then we also know a little bit about what controls the rate, good leaving groups. In the case of both, a good leaving group is always good. For the SN1, a substrate that can tolerate a carbocation is also going to help increase the weight. And then we also know that the SN2 will never happen on a tertiary carbon. And we know that SN1 will never happen on a primary carbon. Right, so that we know that information about those reactions. All right, let's look at some examples real quick. Let's see what we can do with that. And let me go through these through the leaving groups also real quick. So this leaving group right here is what we call a tosylate. Sometimes you'll see it abbreviated as OTOS, OTOS, right? And then this leaving group right here is a triflate. You'll see it abbreviated as OTF. Right, and the way I don't know if we went over this or if you went over it in part one, but the way you tell how good the leaving group is, I think we talked about it Friday actually, how you can tell how good the leaving group is based on the pKa of its conjugate acid. So when you're comparing, like if you're doing an example where you're comparing two reactions and the question is about the rate of reaction, one of the ways that to determine which one will react faster is based on which one has the best leaving group. So let's look at an example of that. I got an example here, right here. Perfect. So let's run through. We'll come back to this part, but let's run through here. So if we look at the two reactions at the bottom, let's see if we can figure out what's going to happen. And the first question asks, what mechanistic pathway would you expect the following reactions to follow? It's kind of redundant, but it's okay. What do you think? So let's do the ICE method. So we identify, we characterize, and then we execute. So let's look at what kind of substrate do we have? Is it primary? Is it secondary? Is it tertiary? Is it allylic? Is it benzylic? Like that's the question you're asking about the substrate. So you look at the substrate, the solvent, and the products if you have it. So what kind of substrate? Where's the leaving group? I guess a better question is, what type of carbon is the leaving group attached to? That's what that question is really.
Secondary.
I heard somebody mention it. I know it's Monday.
Secondary.
Secondary.
Good. So it's a secondary substrate. You know that secondary can go either way. It can be SN1 or SN2. So we need to look at something else. Let's look at the solvent. Right? What type of solvent is acetone? Is it a protic or aprotic?
Aprotic.
Right.
So you got an aprotic solvent, you got a secondary carbon, and then look at the products. What do you notice about the products? compared to the starting materials?
Oh, they both come in from the back.
It's inverted, right? These are
Yeah.
it's two separate reactions, by the way.
Oh, wait. Oh, okay.
Because if you notice, you got two different leaving groups over here. You got a tosylate and you got an acetate. Right? So it's two different reactions. But the what you said is true. They're both inverted. Is that right?
Mm-hmm.
So what mechanism does that point to?
SN2.
SN2. Right, so inversion of stereochemistry, aprotic solvent, secondary substrate, all of that points to the SN2 mechanism. All right. So let's see if we can answer these questions. So we can answer that question and say that it's SN2. Then the next question asks, based on the answer to the question, it should be question 2. What's the correct rate law? What's the rate law for SN? What does the 2 stand for in SN2?
Bimolecular.
Bimolecular. It means that it's gonna have a 2-term rate law. So neither one of these is gonna be the correct rate law, right? The correct rate law is either gonna be B or D. Why is it not B? Is the solvent a part of
Because the solvent's not part of the.
Right.
Yeah.
So the solvent does not control the rate. So that's out. So the right rate law is here, right? K times the substrate, concentration of the substrate, and then the substrate concentration of the nucleophile, sorry. All right. All right, let's look at another part of this question. It says here, knowing what we know about the rate, I'm gonna keep the rate law so you can see it. It says that the concentration of sodium methyl sulfide is decreased 10 times. What happens to the rate? What do we know about the rate law? Whatever I do to the substrate or the nucleophile affects the rate. Is that right?
Mm-hmm.
So how would you answer that question?
If it increased by 10.
You said it would increase by 10. If I decrease.
No, oh, and it says decrease. I'm reading the question wrong. Decrease by 10.
If I decrease the amount of the nucleophile by 10 times, right, it should decrease by 10. Is that right?
Yeah.
Whatever happens there has to affect the.
It affects the overall rate. That's right. All right, we're okay with that? All right,
Yes.
let's look at another question. This is not related to that question, but we're gonna come back to it because I think there's a, yeah. So what do you think here? For number 5. It says reaction of 2-methyl, 3-bromobutyl benzene with sodium ethoxide, right? So this is my nucleophile. And then this is my substrate. This is my leaving group. I'm doing this in ethanol. You following? In ethanol. This is a secondary substrate, by the way. And I'm doing it in ethanol. What is that telling me if I'm doing it in ethanol? Is it SN2? It's a substitution. Is it SN2 or SN1? What type of solvent is ethanol? Is it protic or is it aprotic? Jeopardy music.
Is it April?
It's protic.
It's protic. All alcohols are protic. Let me go back to, what's this calling me? You know I got class. All alcohols are protic. Let me go back to that solvent list. See right here? protic solvents are listed all right here. All alcohols in all caps are protic. So anytime you're using ethanol, methanol, isopropanol, butanol, whatever, that's a protic solvent. All right. So let's go back. What do you think? What mechanism is happening? Because you can't answer the transition state part without answering the mechanism part.
SN1.
SN1.
SN1, very good. So this is SN1. What else gives it away? What do you notice about the products?
Invert.
And then they're both.
I mean, two products.
You racemized, didn't
Yes.
you? Right, you got racemization of your products. All right. So that racemization means that it went through an SN1 mechanism. All right, so now let's finish the question. It says choose the best representation of the transition state of the reaction below, from the list below. So the transition state is referred to as for the rate determining step. All right, what do you think? Let's think about the mechanism now. So here is my starting material. And then my leaving group is going to leave, right? And that's going to leave me with this carbocation. Uh-oh. This intermediate, is that right? So if I'm doing an energy diagram, I'm trying to show this part of the mechanism. The transition state, going from here to here, from the reactants to the intermediate. So what transition state do you think will represent that? Keep in mind this, everybody agreed that it was SN1. Is that right?
Mm-hmm.
So in SN1, the first step, the rate determining step, is what?
Wait, the first step?
Mm-hmm.
Rate determining step is when the leaving group leaves, right?
When the leaving group leaves. Great. So what's happening going from here to here, to the transition state in that first step?
It's gonna speed up.
We're not talking about the rate now. We're talking about what's happening in that step.
So the leaving group leaves. And then
The leaving group is leaving. So what does that mean? It means I'm breaking the bond between what? The carbon, where the leaving group is, and the leaving group itself. Is that right?
Yes.
So we got 4 choices here. We know that in the rate determining step, the nucleophile is not involved for the SN1 mechanism. Is that right?
Yes, sir.
Yeah, it's not involved, right? That's why it's a one-term rate law. So the transition state is going to look like one of these. It's either going to be 3 or 4.
3.
The reason it's going to be 3 or 4 is, again, what's happening in the transition state is that's where your bonds are broken or formed, right? And it can be a lot of bond breaking and bond making if it's a late transition state, or it can be partial, or not. Let me not say partial because it's all partial until you actually get to the product or the intermediate, or it could be limited bond making and bond breaking in the transition state. It just depends on if it's exothermic or endothermic. So which one of those are you going with, 3 or 4? We know that the transition state is going to look like something like one of those. The bromine carbon bond is breaking, right? So we show it as a dashed, partially broken bond.
Would it be 3?
Why'd you pick 3? You're right.
Because if it's partially, I know when I watched the video, it said that there's like a neutral type of charge.
Right.
Going on.
You're right. But look at how the charges are oriented, right? So the carbon is partially positive, which is what you expect, right? Because when you break the bond, it becomes fully positive. Is that right?
Mm-hmm.
And then the bromine, keep in mind, it's got three lone pairs around it, and it's leaving, so it's taking a pair of electrons with it. So that's why it should be partially negative. Your leaving group is always going to be either, if it's positive when it leaves, it's going to become neutral. If it's neutral when it leaves, it's going to become negative, right? So that is the best representation. What's wrong with 4? What's the problem with 4?
Not showing the charge of the carbon, and then bromine wouldn't be positive if it's taking.
Bromine is not going to have a positive charge if it's taking a pair of electrons. I'm going to write this in. Must be negative. Uh-oh, sorry about that. Right, that has to be negative. All right, any questions about that? That problem covered a whole lot of ground with just one example, right? So we're learning to recognize what solvents favor which reactions, the characteristics like the racemization, the substrate being secondary or primary or tertiary, and we also got a chance to look at the mechanism in a little bit more detail, right? You always want to think about the mechanism, how it's happening, right? We know what happens. We know how to do a substitution. We just pop off bromine and put the nucleophile on there. But we also have to think about how it's happening. All right. Any questions about this? About anything? No? All right. Well, let's work some more substitution examples then. Let's see. Oh, yeah. Perfect. This is perfect. Let's do 7. Let me see what's after this. Yeah. We're going to do a bunch of these. All right. Let's do 741. And I'm going to send you a video today dealing with these problems, 749 and 755, ranking nucleophiles. I'm going to send you a video about that today. It's actually like 2 videos back to back. Let's do 741. We're going to do 741, 742, and 743. Let's do that. Okay, so let's look at the on 741. What you're doing is you're comparing substrates, and the question is, which will react more rapidly in an SN1, right? That's very important because depending on the type of reaction, that's going to determine the suitability of a substrate to undergo that reaction. So this is talking about SN1. So let's look at A. What do you think? Which is going to be faster? And tell me why you're thinking about that.
I say the one to the right just because it's like it's more easy accessible.
Ooh, okay, you're right. It is more accessible, but what is the first step in an SN1 mechanism?
Well, also the leaving group.
Followed by what?
The rate determining step.
No, that is the rate determining step.
Oh wait.
Nucleophile attack.
Okay, so when you lose the leaving group, what are you left with?
Left with like an open positive charge.
A carbocation, right?
Yes.
Do you want to put a carbocation on a primary carbon?
Oh, that's primary.
Sure is. No.
Yes, you'd have it on the.
You don't want to do that, right? That's one of the worst carbocations you can make. So this one is going to be faster.
I didn't even know it was primary. I'm tripping.
Yeah, right. Because it's the carbocation that you make is going to be more stable.
Gotcha. I forgot about that. Thank you.
You got it now?
Yeah, I forgot about that rule.
Uh-huh. All right. So the tertiary one is going to be faster because when the leaving group leaves, you get a more stable carbocation. Right? Let's think about that. So for SN1, it's not really about accessibility, it's about stability. Right? That's the guiding thought. Right? Stability of the carbocation. That's what you're thinking about in all of these examples. Why? Because the question asks you which one will be faster for SN1. So now you know you already have your concept laid. Oh, it's SN1. We know that it's going to make a carbocation. So that's what I'm looking for. Which one of the two substrates is going to give me a better carbocation? Or which one has the best leaving group? You follow me? One of those two things is going to guide that. All right, we're good with that? So let's do B. We can finish these. We got plenty of time. Let's do B. What do you think? What substrate is better suited for SN1?
Second one.
Second one.
Yeah, the second one.
This one. Is that right?
Mm-hmm.
Again, you got a tertiary substrate versus a primary substrate. The leaving group is the same for both, so you don't have to compare that. All right, what about, so this one, I'm gonna circle it. What about C?
The second one,
Second. Why you say that?
because it's able to have a second resonance.
Oh,
structure.
say that again, I couldn't hear you.
Has a second resonance structure.
Absolutely. So when you compare these two, this allylic substrate, when you make the carbocation, is going to look like this, which can be stabilized. Uh-oh, let me not do that. For that. Get it together, Russell. It's going to be stabilized by resonance. Right? So this is going to, the allylic substrate is going to be faster. Right, that allylic substrate is going to be stabilized by resonance. So that's going to be a better substrate for SN1. Let's keep in mind what you want to do for the SN1, the very first step is the loss of leaving group. All right, what about the last one? What are you comparing in there in that case?
The better leaving groups.
Leaving groups are different, both on tertiary substrates. So now we need to figure out which one is better. So let's go back up to our list. Wherever it is. Oh, here we go. What was it? Tosylate and what was the other one? Chlorine?
Yeah.
Mm-hmm.
So chlorine is here. And this conjugate acid has a pK of -7. And then the tosylate has a pK of -0.6. So which one has the lower pKa?
Chlorine.
Chlorine, right? So when we compare those two leaving groups, chlorine is a better leaving group. It's a better leaving group. What does that mean when you look at the conjugate acid pKa? What does that mean for Cl minus? I know we went over it, but I want to kind of drill it. Like, what does that mean for the Cl minus? If the
Are you asking like it's which one's like the strongest? I could be wrong. Sorry. Like
speak up.
you were like at the beginning we were talking about the pKa of the conjugate acid will tell us which one's the strongest leaving group, right?
Yeah, but also it also tells you something else too, though. If the conjugate acid has a low pKa, that means Cl minus is okay being negative, right? It means it's a better conjugate base. That's what those two go hand in hand. That's the point I was trying to get to.
Okay.
Right? So the conjugate base is more stable if the conjugate acid pKa is lower. Right? So that means that when it leaves, it's okay being by itself and having a charge on it if there is a charge involved. All right. Let's go back to here, right here. All right, so we said the chlorine had a pK of -7, and then the tosylate had a pK of -0.6. So chlorine has the conjugate acid of the chlorine has a lower pKa, which means that chlorine is a better leaving group. We're okay with that?
Yes.
All right. Let's go over to 742. Because all the other ones are, we're going to start on elimination Wednesday. We'll spend Wednesday and Friday doing that. So 742. Let's look at this reaction, see if we can figure it out. It says consider the following reaction. So you got this, let's see, 1-bromo, 2,2-dimethyl cyclohexane, and you reacted it with sodium cyanide, which is when you see a sodium in there, all right, as a rule of thumb, you can write it as a salt, so you'll know exactly what the nucleophile is. Whatever atom sodium is close to, that atom is negative. So this CN, hold up. Yeah, so that cyanide is actually negative. All right, so this is your nucleophile. And there's a lone pair on nitrogen as well, right? All right, so let's do the ICE method. Let's identify. So what kind of substrate are we dealing with? Primary, secondary, tertiary? What is it?
Secondary.
Secondary.
Speak up now, don't be scared.
Secondary.
Secondary, right? It's a secondary carbon, right? Got a good leaving group. Bromine is an excellent leaving group. What kind of solvent is DMSO?
A product?
Say that again.
A product?
It's aprotic. Good. I can't stress it enough. You need to look at that list and commit those solvents to memory, right? At least memorize that part. It's not that, the protic ones are easy. All acids, all alcohols are protic. But the aprotic ones, you're gonna have to commit them to memory. So DMSO is aprotic. And then look at the product. What do you see in the product?
Inversion of
Stereochemistry. Right, you see inversion of stereochemistry. All of that points to what? What type of substitution is this? Is it an SN1 or is it SN2?
2.
It's SN2. Good. Once you know that, you can answer the questions. How would the rate? So what is the rate law? Let's write that out.
Dr. Russell,
Yes.
and can you not have inversion SN1? I thought we've had that before, or maybe I'm thinking I got those confused.
Say that again. Not for SN2.
No, for SN1.
It depends on. So inversion happens if you got a chiral center present, right?
Okay.
It's not. So only when you have a chirality in play do you see inversion. Otherwise, you're just gonna get two products anyway.
Okay.
For SN1. Right, the SN2, sometimes if it's on a Like if it's on a primary carbon, you're not going to get inversion because that primary carbon is not going to be a chiral center. The only time you're going to see that really is if it's on a secondary carbon that's not symmetrical. You see how like on this molecule, you got like if these groups weren't right here, then that bromine wouldn't be a chiral center. But because those methyl groups are there, that makes it chiral, so that means when it goes through the substitution process, it's going to get inverted because of how the nucleophile is still going to come in opposite of where the leaving group is no matter what.
Right, okay.
Yeah. But you're always going to see that especially on a secondary carbon. So substrate and then nucleophile. Sorry about that. K times the concentration of the substrate times the concentration of the nucleophile. All right. So let's do A. What will happen? How will the rate be affected if the concentration of the alkyl halide is double? That's your substrate. If I double the concentration of the substrate, what's going to happen to the rate? And I keep the concentration of the nucleophile the same. So that's like saying if I put a 2 here and a 1 here, what's going to happen to the rate?
You're going to double?
The rate should double, right?
Gonna be doubled.
Let me erase that part. Rate will double, right? What about B? Consider the following reaction. Oh, never mind. That's the next question. B says, how would the rate be affected if you double the concentration of the nucleophile, sodium cyanide? What would happen?
It would be doubled as well.
It would be doubled also. That would be like keeping the substrate the same and doubling the nucleophile. Right? Keep in mind that that rate is a product. So the concentration of the substrate, concentration of the nucleophile, those are multiplied. So if I double one and keep the other one constant, then the rate should double. If I double them both, the rate should quadruple. Right? If I triple them both, the rate should increase by 9. All right, let's go to the next question. Same type of question, but let's do the ice method. What type of substrate am I working with? Is it tertiary, secondary, primary?
Tertiary.
Tertiary. That's a giveaway, right? If it's a substitution and it's on a tertiary carbon, it cannot be SN2. It's got to be SN1. SN2 will not happen on a tertiary carbon because the carbon, the accessibility of that carbon is minimal to the incoming nucleophile because it's got to come from the opposite side of where your leaving group is. If it's a tertiary carbon, the back side is going to be blocked. Right? Let me show you. So if I got a tertiary carbon, and here's my leaving group, and this is my nucleophile trying to come in, that's not going to happen. Right? It's too much steric hindrance for that to happen. So if you see a tertiary carbon and you see the product being a substitution product, you know that it's SN1. It cannot be SN2. All right, so let's answer those questions. What's the rate law for SN1?
Just the substrate.
Just the substrate. Very good. K times the concentration of the substrate and that's rate. All right. So how would the rate be affected if the concentration of the alcohol, that's your starting material, your substrate, is double? What's going to happen to the rate?
It'll double.
It should double. Good. What about B? What if I increase the concentration of HBr, which is the source of my nucleophile?
Nothing will happen.
Nothing. Good. Good. Nothing is going to happen because the nucleophile is not involved in the rate determining step. Nothing. With 3 exclamation points. All right, 7:44. Let's do this real quick and we're going to stop because I got to call my cousin back. I think that's his mom is in the hospital, so I got to call and check on her. 7:44. Classify each of the following solvents as protic or aprotic. We should be able to do this quick. Ethanol and water. Let's do those. Protic or aprotic?
Protic.
Protic.
Both protic, right? DMF and DMSO.
April.
Speak up.
Aprotic.
They're both aprotic. So is ammonia. I know you want to think about ammonia being protic because it's got 3 protons on it, but they're not acidic. The pKa of a nitrogen bound proton is somewhere in the 30, anywhere between 30 and 50, depending on what else is on nitrogen. So this is also going to be considered aprotic. So all the pink ones are aprotic and then the green ones are protic.
Wait, so alcohol is the substrate. That's why if it is doubled, it will double the reaction.
Yes. And then HBr is the source of your nucleophile. It's not a nucleophile per se. But once you go through the mechanism of proton transfer and then loss of leaving group, the bromine ends up being a nucleophile. We've already done that. Actually, remember when we did addition of HX to an alcohol a couple of weeks ago? Right, we know that mechanism goes through it's a substitution type mechanism, and it goes through a carbocation intermediate. Are y'all following? You're gonna have to go back and check your notes on that one. All right, we're gonna stop here, and then I'm going to chop. Well, I don't have to chop this up, but I can upload it and upload the notes to Blackboard. Any questions?
No, thank you.
All right. I'll see y'all Wednesday, God willing.
Yes.
All right. I appreciate y'all logging in and being attentive, and I'll post everything we need to post after this is over with. And I'm gonna start grading those tests today too. Now, were y'all able to go back and look at your exam to see what you missed? Because I had to turn on a function so nobody else could submit it, but the exam will still be available so you can see what you got wrong or what feedback I gave or whatever.
Yes, sir. We were able to view.
Okay. All right, cool. That's all I want to hear. All right. I'll see y'all Wednesday.
Bye.
Okay. Have a good day.